Good morning, everyone. My name is Arwa, and today I'm going to present our work titled Privacy-Aware Split Learning-Based Energy Theft Detection for Smart Grids. This is a joint work with my supervisors, Professor John Clark and Dr. Prosanta Gope from the University of Sheffield. In today's presentation, I'll start with explaining the research problem, which was the motivation behind this work. Then I'm going to highlight the different types of privacy-preserving machine learning, focusing on split learning. I will then describe our proposed detection model, the simulation and results, and finally concluding remarks will be given at the end. A very important issue in smart grid is data privacy. So why do you think we need data privacy in smart grid? As you all may know, smart meters that are installed in every household transmits fine-grained data to the utility servers every 15 to 20 minutes. This actually poses huge risks to data privacy because analyzing these data can reveal valuable information about the daily behavior of someone's life. If you see the figure to the right here, you can clearly see that analyzing the consumption of this person can reveal when he was sleeping, when did he wake up, and when he left the house. Another great problem is that these information are not only shared with utility services, however, they can be sold to third-party companies for marketing purposes. This leads us to an important thing, that the privacy of users' data should be protected at all times, specifically while data transfer, which is our focus today. Data privacy can be achieved using one of these four mechanisms, either by data obfuscation, encryption, differential privacy, or privacy-preserving machine learning technique, which is our main focus. Existing privacy-preserving machine learning techniques can be divided into three subcategories. The first is cryptographic-based approaches that uses encryption such as homomorphic encryption. Data can be processed in machine learning models while they are encrypted. The second type is the federated learning approach, where each client trains a local model using its own data and then share the model parameters with a global server without sharing the data. Finally, we have the classical split learning. The classical split learning works by splitting a machine learning model between the client and the server, where clients process their part of the model and the outputs are transferred to the server for further processing. Despite the advantages of those privacy-preserving machine learning techniques, they have some shortcomings. For example, in the cryptographic-based approach, they rely on cryptographic keys and their management, and they often have large ciphertext. And some of the cryptographic approaches are limited to certain types of computation. For the federated learning, there is high possibility of data leakage because the whole model is shared. Another problem is that the machine learning should be trained in full at the client side. For the classical split learning, one of the shortcomings is that the machine learning model can be poisoned by untrusted clients. On top of these privacy and security issues, these approaches are either complex, for example, as in the cryptographic-based approach, or introduce communication overhead, and this is in case of the federated learning. Another problem with the classical split learning, even though it was emerged as an approach to resolve the existing shortcomings of the state-of-the-art solution, it cannot be directly applied to smart grids. Here is a comparison summary between the three types of privacy-preserving machine learning techniques in terms of privacy preservation, non-reliance on cryptographic keys and their management, the computational and communication efficiency, and the ability to be directly applied to smart grids. As you can see, none of these approaches can be directly applied to smart grid, and that's why we have introduced our work. So, because data privacy is very important and because of the shortcomings of the existing privacy preserving machine learning techniques, we have three main contributions in our work. We are the first work to apply split learning to energy theft detection, and we are including prosumers as users in the system. We're also proposing a new variant of split learning, which we call three-tier split learning. This is because the classical split learning cannot be directly applied to smart grid. Another issue with the classical one is that it introduces higher communication. So in our new variant, we lower the communication overhead through aggregating the updates from the split layers. The third and final contribution is that we analyze the privacy of the proposed model in terms of feature leakage using a metric called distance correlation. Now I'm going to explain some preliminaries where I'm explaining the concept of federated learning and split learnings in details. So what is federated learning? Federated learning is a collaborative machine learning approach where each client trains a local model using its local data and then share that local model with the global server. As you can see here, there is no sharing of the data, only the model are shared between the client and the server. And at the server side, all the local models are grouped together using aggregation. Another type of collaborative machine learning techniques is the classical split learning. In the classical split learning, we have the whole machine learning model is cut into two parts. The first part of the model resides at the client side, while the second part of the model resides at the server side. Each client uses its own input data to process its part of the model, and then the output of the cut layer are sent to the server for further processing. As we said before, this classical split learning cannot be directly applied to smart grid, so that's why we're introducing our new variant, which is called three-tier split learning. Here is a figure showing our proposed three-tier split learning. As you can see, the machine learning model is split into three parts instead of two. The first part resides at the client side, the second part resides at the aggregator side, and then we have the final part resides at the server side. Another issue that we're considering in this variant is that we minimize the overhead of the communication. So instead of the aggregator processing each of the client's outputs in a single iteration, we have the aggregator waits for all the client's output and then it uses them as a single averaged input to its part of the model. The same goes for the server. The server waits for all the aggregator's outputs and then average them and uses the average of all the aggregator's output as a single input to its part of the model. In this slide, we show the system model that we're employing in our proposed approach. It's a typical smart grid environment where we have three major components: the smart meters, the aggregators, and the server. As you can see, we're employing the three-tier split learning. So we have part of the model resides at the smart meter part, and part of the model is at the aggregator side, and the final part is at the server side. Smart meters do not directly share the smart meters data. However, they share the activations or the output of the split layer. The aggregator also shares the activation of its split layer. The final part of the model is the server, where the server continues the processing and output the anomaly detection, whether the data is as energy theft or not. In our model, we consider 3 types of attacks. The first one is the energy theft attacks. The second one is poisoning attacks. And finally, we're considering feature leakage or reconstruction attacks. The first attack in our threat model is the energy theft attacks. These attacks represent any tampering that happens to the smart meter data at the client side, and this happens only at the deployment phase. If this tampering happens at the training phase, then we call it a poisoning attacks, because any tampering that happens at the training phase actually aim to mislead the model and the detection model. So this is what we call by poisoning attacks. The final set of attacks that we have is feature leakage attacks or reconstruction attack. In these attacks, the attacker tries to sniff or eavesdrop the activation that are sent between the client and the aggregator, or the communication channel between the aggregator and the server. By doing so, the attacker tries to infer the original data from those activations. In order to evaluate our proposed detection approach, we've used a number of experiments using this experimental setup. For the dataset, we've used our own generated dataset using an emulator called GridLabD. GridLabD is a smart grid emulator, and in our emulation, we had 1,600 clients. 49 of those were prosumers with solar panels. For each client, we had 13 physical features that characterizes the client property, and every smart meter reported 17 dynamic features every 15 minutes. In all of our experiments, we've used a sliding window of 16 data points, which equates to 4 hours. The whole 17 dynamic features, along with the 13 static features, were used in this sliding window. The dataset was split into 70% for training and 30% for testing. And we've used a feed-forward neural network of depth 10, where 3 layers reside at the client side, 3 at the aggregator side, and 4 at the server side. And we've used PyTorch for all of the coding. This is the first set of results that we got in terms of energy theft attacks. We have measured the accuracy, recall, or what is called detection rate, and the precision. In all of the experiments, we trained a neural network model through 20 epochs, and we compared it to the centralized approach and the federated learning approach. What do we mean by centralized approach? Is where the machine learning resides at the server side and the processing is only done at the server side. So there is no privacy guarantee. As you can see from the results, the results are comparable to each other and almost equal to each other in all of the 3 approaches. This is the second set of results in terms of the second attack in our threat model, which is poisoning attack. So we tried to see how resilient our detection approach is against poisoning attack. And as you can see, we measured the accuracy, recall, and detection rate, and the precision. We started with the case with no poison data at the training data, so which means there is no attack. We then increased the percentage of poisoned data from 0 to 20%. As you can see, as the percentage of poisoned data increases, the accuracy and recall drops. So we need to have a solution for that. A simple solution was to randomly drop 10% of the inputs at the aggregator side and at the server side. So by randomly dropping 10% of every aggregator and client's input, we can get an accuracy of 0.93, which is comparable to the case where there is no attack, as you can see at the first row. Also, the recall is comparable to the non-attack case, and the precision is almost the same. For the feature leakage attack, which is the final attack in our threat model, we did some privacy analysis. In this experiment, we tried to see how much the activations or the output sent by the client and by the aggregator can actually reveal the original data. So we need to measure how much these activation between the client side and the aggregator and between the aggregator and the server can actually leak data about the original data. So we tried to measure a metric called distance correlation. Distance correlation is a statistical measure that shows both linear and non-linear association, and it shows how two sets of arbitrary dimensional vectors are dependent on each other. For example, in our case, we measured the distance correlation between the activation sent by the client and the raw data, and the activation sent by the aggregator and the raw data. Distance correlation takes a value between 0 and 1, where the lower value indicates greater independence. So in our case, the lower the number, the better it is. Here is the results of the distance correlation. In the second column, we've measured the distance correlation between the raw data and the activations or the output sent by the client. In the third column, we've measured the distance correlation between the raw data and the activation or the output sent by the aggregator. And in all of our cases, we tried to monitor the theft detection because we don't want to compromise theft detection while we're lowering the distance correlation. In the first set of experiments, we've used a model of 3 layers at the client side, 3 layers at the aggregator side, with no dropout layers in between. And as you can see, the distance correlation between the raw data and the outputs of the clients are very high, which is 0.74. So we needed to make sure that this number is lower. So we did some more experiments. We added more dropouts. As we add more dropouts, the distance correlation lowers. And when we actually add more layers at the client and the aggregator side, the distance correlation also lowers. So if we only had 4 layers at the client side and 4 layers at the aggregator side with 2 dropouts in between, we get a distance correlation of 0.49, which is almost as random guessing, which means there is almost random guessing probability between the raw data and the outputs of the client. And as you can see, the theft detection hasn't been compromised while we're lowering this distance correlation. In the last set of experiments, we did some communication analysis to make sure that our proposed 3-tier split learning is not introducing any communication overhead. We compared our three-tier split learning with the classical split learning and the federated learning approach in terms of communication per client and total communication. As you can see from this table, the three-tier split learning has the same communication per client as the classical split learning because we haven't made any changes to the way clients work. However, both the split learning approaches are much superior to the federated learning approach in terms of communication because they only share the output of the split layer. In the federated learning approach, the whole model is shared, which means more communication. In terms of total communication, our three-tier split learning is superior to the classical split learning approach because we use the notion of averaging and aggregating. So instead of using the intermediate layer, such as a relay in terms of the classical split learning, we're using it as an aggregator where we aggregate all of the client's output into a single input. In terms of the classical split learning, in case of the classical split learning, the intermediate component in the smart grid works as a relay that transmits every client's output to the server. So that's why our three-tier split learning is much superior in terms of the total communication, as it reduces the communication between the intermediate layer, the aggregator, and the server side. And here is a summary of the results that we have just shown. We've compared the three approaches of the centralized approach, the federated learning approach, and the three-tier approach in terms of energy theft detection, privacy preservation, resilience against poisoning attack, resilience against feature leakage attack, and communication efficiency. To conclude, we have proposed a new variant of split learning, which we call three-tier split learning. The three-tier split learning is much more suitable for the nature of smart grids environment. Another important thing to remember is that data leakage attacks are very serious and need to be addressed in any privacy-preserving approaches. Unfortunately, they are often overlooked. We have used distance correlation as a measure to assess leakage attacks. The reason that we use distance correlation is that because it can measure the association between two arbitrarily linked variables. Thank you for your time. I would be happy to answer any questions that you have. Thank you.